So here what we're looking at is the X-ray computer. And so it's interfaced with the X-ray diffractometer. So earlier what I was explaining was how to mount the crystal. So what I was trying to tell you is that the crystal, the optimal size of the crystal is generally 100 microns. That's the best size for the crystal. And that's because the most intense part of the X-ray beam is this little circle here, which is 100 microns. So the most intense part of the beam is 100 microns. And so that's why 100 micron crystal in any direction is preferred. Now you can go beyond 100 microns. I mean, you can go up to about 300 microns. So to give you an idea, 100 microns is like 0.1 millimeters. 300 microns is like 0.3. And so if I was to go down here and change the size of the beam from 0.1 to 0.3, that'll give you an idea of the maximum size of the crystal. So the pink circle here represents 300 microns, which is about the full width of the X-ray beam. Now the most intense part of the X-ray beam is this green circle, which is about 100 microns. And so it's ideal to have a crystal that is 100 microns or 0.1 millimeter in every direction. And so to see the outline of the crystal I have mounted, it's like a triangle looking shaped crystal like this. And so what you're supposed to do to mount the crystal is the crystal is mounted on the axis referred to the phi axis. The phi axis is the axis that rotates the crystal. And so once you put your crystal on what's called a nylon loop, so the nylon loop is right here. I don't know if you can see it because of the glare, but the nylon loop is situated right here. And that's the nylon loop. And then we coat it with a film of very thick oil, and you stick the crystal to the oil, and then you put it on the diffractometer. And so we're going to rotate about the phi axis to align the crystals. So we start at 0 here, and when it's at 0, let me open up the machine and show you. We have to align it so that the crystal, the center of the crystal is in the middle of that circle. So we can move it left and right, and we can move it up and down to align it so that the center of this circle is in the center of the crystal if the crystal is bigger than the circle. And then once we center it at 0 degrees, we go and we center it at 90 degrees. So 90 is orthogonal or perpendicular to 0, so then you try your best to align it if you can. Move it left and right. And then you keep on going back and forth between 0 and 90 degrees until the crystal is perfectly centered. So this crystal is now centered. You get the shadow there. And now it's ready to be screened. So screening the crystal tells us whether this is a good quality crystal or not. That's what we're going to do next, is screening the crystal. Oops. Let's see, lost connection. One second. Okay. So now the crystal is centered, we're ready to screen the crystal. We're going to exit. And now before we actually do the screen, let me explain some of these parameters here. And so the first parameter is called the theta angle, and the theta angle is the angle at which you want the detector to be at. Because when you're screening the crystal, the detector, everything is set at one fixed position. There's no rotating going on when you're doing the screening. And so just my preference, I like to screen at a negative 35 degrees to theta, but most people like to set this to 0 degrees theta. It's just a preference, whatever you like. The general is 0. I like negative 35. As far as the different options here, the phi offset and the scan axis, these are default. I don't change any of those. And then detector distance, usually you set it to very close detector distance. I set it to 36 millimeters. The shortest detector distance is 35 millimeters. So the distance between the crystal and the detector, the shortest you can get is 35 millimeters. I set it to 36. Exposure time, you can set to what you like. This is dependent on the type of crystal. Does it contain a lot of heavy atoms? Is it a large crystal, small crystal, etc.? And so since I know this is an organometallic complex that I'm looking at, I'm going to set it to a very fast exposure time of 0.5 seconds. So once you've got all of these set, you're ready to screen the crystal. So what you're looking for when you're screening the crystal is that your diffraction spots, these black spots that appear on the image, have a nice shape to them. They're circular. They have, they're not smeared. They don't have what we call sister spots. And so from this diffraction, this screening, we can see that these diffraction spots look very clean because they're very, well-defined diffraction spots, and it just kicked me out for some reason. Well, this is a disaster. Why does it keep on kicking me out? Yeah. And so now that we have these good diffraction spots, this looks like a pretty decent crystal. The other thing you want to look at is from doing these 20 different pictures of the crystal, we determined that there were 78 spots, so diffraction spots, and it accepted 78. So we have an acceptance of 100%, which is a beautiful crystal right there. The minimum you need is usually 12 to 15 spots in screening. And so from those 20 images, it was able to determine the point symmetry group 2 upon M, the unique axis of B, and it was able to determine the crystal system monoclinic, and it's going to be a primitive lattice, all from these 20 fast screened images we just did. In addition to that, we got an initial unit cell. And so the reason it thinks it's monoclinic is because A, B, and C don't equal each other. Alpha and gamma are very close to 90, so it's suggesting a monoclinic space group or crystal system. Now you'll see that the point symmetry is 2 upon M. So 2 upon M indicates that this might be in a centrosymmetric space group. And then over here we just see the resolution and the quality of the diffraction spots. And so what you look at for quality of diffraction spots is the I over sigma. So the higher the I over sigma, the better quality data you have. So, and you mainly look at the highest resolution, and we have 19 spots and about 8.2. 10 is the best number, but you got to remember we only did a half-second scan for the initial screening. So from the screening, we gathered that it is a decent crystal. So now we can move on to the pre-experiment. And now what the pre-experiment does is that it determines the best parameters to do a full data collection. Now we'll get to the pre-experiment, but just to kind of show you how you go about collecting data, solving structure, we're actually going to click on a button this time, which is called "What is this?" And so we're going to click on it, and it's going to tell us what this crystal is here. So let me click on it. And so we want to at least give it the types of elements in the complex. So we know there's cobalt, there's sulfur, nitrogen, oxygen, carbon, and hydrogen. So these are the elements in the organometallic complex. And once we hit start, it's going to determine what is this. And it's going to be probably in less than 5 minutes, it's going to determine it. That's how powerful this analytical tool is. So when I hit start, it's going to try to do a series of different scans to determine what is this organometallic complex. And you're going to see over here in the right-hand window, it's going to start solving the structure automatically. So it's doing a variety of different scans. So right here where you see the shutter is open, that means X-rays are being emitted. So this is shutterless technology, so the X-ray stays open while it's collecting data until it needs to rearrange the different angles for the crystal. And we'll talk about those angles probably next week when we talk about the glucometer. So now it's moved the crystal or moved the crystal to orient it differently. It's collecting a new set of diffraction images. Now it's starting to solve the structure. So if you look in that little window, the computer, based on the diffracted images, is solving the crystal structure. So just to give you a little rundown, the metallic looking atom here is a metal, and that's going to be actually cobalt. The blue colored atoms are nitrogens. The gray represents carbon, and the red represents oxygen and yellow sulfur. Of course, white represents hydrogen. So now it's going through, it's solving this structure, trying to tell us what it is. And I haven't been talking more than 3 minutes, and it's almost done by looking at the progress bar. So within 3 or 4 minutes, we've determined the structure of this compound. And this is actually, for those who took Jenkin 1 lab, this is actually a Sachrinate complex. So you'll see that that's a Sachrinate anion, and the complex is with cobalt. So this is a cobalt Sachrinate complex. So just trying to finalize up the structure. But while it's finalizing, let me make a few points here. So the space group, you notice, it picks space group P21 upon C. So P21 upon C is interesting because remember, it's one of the 5 major space groups that most crystal structures for organometallic complexes fall under. So this is a very common space group here. Now this is space group P21 upon C. Think about this, is this going to be centrosymmetric or non-centrosymmetric space group? So I'll give you a minute or two before I answer that. But again, it's P21 upon C. And so this is actually a centrosymmetric space group because you have a 2-to-1 screw axis and you have a mirror plane perpendicular to the axis for that screw axis. Now, a few other things that we'll touch on when we start solving crystal structures, but this R1 and weighted R2 are kind of like the gauge we use to determine how well we've solved this crystal structure. So R1 and weighted R2 are almost the same thing, but they're a little bit different because R2 is weighted where R1 is not. And so R1 is the difference between the observed parameters and the calculated parameters from the structure. So the better your structure is, the more closely these parameters will fit the observed parameters. And next week we'll talk about what these parameters are. But when you're collecting data, you're collecting a set of observed parameters, and you're trying to fit a model to that data to get a set of calculated parameters from the model that match the observed. So the closer these two are, the lower your R1 is. So it's 2.6% is pretty good. So less than 10% is ideal, but the closer you are to 0, the better the data, the calculated data fits the observed data. So I just wanted to show you a little bit of an excerpt of what's to come when we solve crystal structures. Now, this is a well-known sample. That's why it was very quick, but not all of these samples we find this easily. But this is a good way to see what the structure is. Now, if I open this up in a crystal structure solution software, I can actually show you where the inversion center is. So I click on OLEX 2, which is something you'll be installing. Let me stop the share here and bring in a new share once the OLEX 2 loads up. Oh, duh. Silly me, yeah, hold on a second. There we go. So this is the structure that we just solved by determining what is this. So let me do a few things. Yeah. Okay. So again, this is the Cobalt, but we label these. This is the software we'll be using to solve crystal structures. So you can see the different atoms in the crystal structure. Now remember that this is a centrosymmetric space group. And so that means that there's a center of inversion somewhere in this structure. So the center of inversion we can find by, we'll use a command called grow, and grow generates the other symmetry related part of the crystal structure. So if I do, let me show you again. So this cobalt here, this cobalt sits on an inversion center. And so when I hit grow, we go through the inversion center, we generate the other part of this, what we call centrosymmetric diamond. Again, let me use it. So this is the asymmetric unit, and then we hit grow, and we generate the symmetry-related component to the asymmetric unit. So this is the inversion center we just went through. So let me, so now you see that we have N8, and now we have N8I. So that means N8, this is the inverted atom of N8. Let's see, O13I is O13. So it was inverted. It goes through this inversion center. We generate O13I. So N8, we go through the inversion center. We get the negative of N8, N8I. So this is how you can see where an inversion center Yes. So let's see. That's all I wanted to show you with the X-ray structures. Let me stop this part of the lecture. Hopefully it was interesting.